So now let's talk about the I2C or I2C communication system. It's one of the more common that we will find in these Arduino systems and the sensors and actuators that'll talk to them. It's a pretty good system. You can do a lot with it. And that's partly because the people that designed it, frankly, were quite clever on how they used these just two data lines to do a lot with them. So we're going to walk through some of the basics of how that works, so when you write your code, you know what's going on. The first thing that's cool about the I2C system is there can be multiple masters, that's something that's talking, and multiple slaves, that's something that's listening. That could be two Arduinos talking to each other. It could be an Arduino talking to multiple actuators and listening to multiple sensors. Masters talk, slaves listen in this jargon. There's an immediate problem with this, and you need to understand this in order to not burn up the circuits. And that's, how do you have a line here? The SDA stands for data, DA for data, and the CL for clock. So just like a couple of slides ago, the clock is going to beat the drum whenever data bits are being sent, and the data bits are going to be on the data line. That's all good. But what if the master decides to set the data line low, and the slave over here, one of them, decides to set the data line high? That would be in conflict, and one of those would burn out. So we have a real problem, just in a basic analog electrical engineering design standpoint, of how do we have these different chips all talking on the same wires when they want to set it high and low, zeros and ones. But if any two of them disagree on high and low, then suddenly that wire is going to have a lot of current flow through it, and we're going to burn out one of the chips. And the tricky thing they do is they only set it low. So you see these two lines here. VCC stands for the power supply voltage, maybe 5 volts on your Arduino. And we have a pull-up resistor. These are usually maybe 4.7 kilo ohms that goes to each of the clock and data lines. And for example, if this master is trying to modulate the clock with a square wave to beat the drum, what it would do, it would take the line here between ground and I'm not driving it at all. I'm not even connected to it. Basically, I open a switch. Well, when I set it to ground, there will be a little current that will flow, but I will have ground, resistor, and my power supply. That's okay. Nothing's going to burn up there because this resistor is going to keep me below maybe a milliamp or so of current. If I have 0 volts, 5 volts, and about 5 kilo ohms, I get about a milliamp. And then when I disconnect, the line will go high because there's no current flowing anywhere. These are all good high resistance ports. So I've got 5 volts, a resistor with no current. So this floats up to 5 volts, or it gets pulled up to 5 volts. So the tricky idea is, when you want to modulate any of these lines, you go between not high and low, in terms of what the internal chip is driving voltages. You go between not connected and low. And if nobody else is doing anything else to the line, when you disconnect, it will go high. If someone else was doing something else to the line, it doesn't cause you to burn out because you're not trying to drive the opposite ends of a wire to different voltages. So an important little detail, and you will see these pull-up resistors on lots of drawings of I2C communication because they need to be there somewhere for it to work. And sometimes you need to know what the value of that resistance is, maybe to get between different voltage standards. Some chips might be running at 3.3 volts, some at 5, and we're actually going to have that. But knowing how this works, you can actually design a little circuit, a voltage divider, to deal with that.